Hello, my dear students. Today we are going to discuss about Markovnikov addition and anti-Markovnikov addition in this video. What do you mean by Markovnikov addition? See, the Russian chemist Markovnikov studied a number of addition reactions, and you can see the scientist here, the Russian chemist Markovnikov. And he suggested a rule called Markovnikov's rule. So what is this rule? See, this rule he has suggested to predict the course of the reaction for addition of hydrogen halides especially, and for the other unsymmetrical reagents such as you can see here, HCl, HBr, HI, HOCl, and H2SO4, etc. to an unsymmetrical alkenes. So this rule is called as Markovnikov's rule. So what is the rule named? Which is stated as in the ionic addition of an unsymmetrical reagent, that is Hg. See, it can be HBr or HI or HOCl or H2SO4. So you can take any unsymmetrical reagent where the hydrogen or the positive end of the reagent, which will become attached to the carbon atom of the double bond bearing larger number of the hydrogen atoms. So how he was explaining this rule, you can see he is taking the unsymmetrical alkene, that is C double bond CHH, which is added with the unsymmetrical reagent here. So alkenes, when it is reacted with hydrogen halide by the addition across the carbon-carbon double bond to form an alkyl halides or alhaloalkenes. So if you take an alkene, the symmetrical alkene, for example, ethylene, we are going to see. So alkene generally, which is added with the hydrogen halide here, HX. So which can form an haloalkene, alkyl halide or haloalkane. Hydrohalogenation. So the reactions involving the addition of hydrogen atom and a halogen atom to the carbons of a carbon-carbon double bond. So this hydrohalogenation, where you can see the reaction involving hydrogen atom and a halogen atom. So this is, you can see here the hydrohalogenation with alkene, which is forming the haloalkene. So now we are going to see as an example ethylene, a symmetrical alkene, which is added to HBr here. So this is an unsymmetrical reagent where you can see ethyl bromide is formed or bromomethane. See, when you take this two butene in the same way, CH3, CH double bond CH, CH3 plus HBr. So when it is added, so this is called hydrohalogenation. So you can see here CH3, CH2 and CHBr, CH3. This is called 2-bromobutane. So what is here? You can see this, the positive end of the reagent can be added to the carbon and the bromine, the negative end of the reagent can be added to the another carbon. So what is the rule was telling us? It can be added on either side, and you can see since this is a symmetrical alkene, it can be added to either to this carbon or this carbon. Next one is we are going to see about addition to the unsymmetrical alkenes. See here the hydrogen halide, the HBr, same reagent only we are taking here, which is added to unsymmetrical alkene here. See ethylene, what we have seen above is symmetrical alkene. Now we are adding this hydrogen bromide to propylene, that is unsymmetrical alkene. Here in this case, two addition products are possible. You can see here. See, the hydrogen atom can be placed on one or the other carbon of the double bond. Propylene is added with HBr to form N-propyl bromide as well as isopropyl bromide. Whereas this isopropyl bromide is formed as a major product. But experimentally, isopropyl bromide obtained predominantly. See, the propylene, which is added with HBr, can give isopropyl bromide as the major product, whereas N-propyl bromide as the minor product. What is the reason? This is according to the rule we are going to see. And then, see, the addition reaction of an alkene, which follows Markovnikov's rule or referred to as Markovnikov's addition. See, in this case, 2-methylpropylene. This is also unsymmetrical alkene, which is carried over with HBr. So it can form 2-bromo-2-methyl propane. So the mechanism in this case, unsymmetrical alkene, in this case, it involves the formation of carbonium ions, addition of hydrogen bromide to propylene. So you can see here, it is giving a cyclic intermediate. Here also the formation of the pi complex, but it is forming a cyclic intermediate, whereas in symmetrical alkenes, we have seen only it can form the pi complex. See, in this, you can see CH2 double bond CH, CH3, whereas this double bond is shifted and then it carries a H plus. So where this positive end of the reagent is attacked by this carbon and it is forming a cyclic intermediate plus Br minus. So the cyclic intermediate, since it is forming, it is capable of forming 2 carbonium ions or carbocations. See, one you can see the secondary carbonium ion where it is forming CH3, CH plus CH3, and then primary carbocation CH3, CH2, CH2 plus. So we know that according to the carbonium ion stability, the secondary carbonium ion is more stable than this primary carbonium ion. So the carbonium ions 1 and 2 react with the nucleophilic bromide ion from the step 1 to give 2 possible alkyl bromides. See, this carbonium ion, the secondary carbonium ion can be added to the negative part of the reagent Br minus, where it can form isopropyl bromide, which is the major product. Whereas in case of primary carbocation, it attacks with Br minus to form N-propyl bromide. As we know, the stabilities of the carbonium ion is in the order tertiary, secondary, and primary. So where the tertiary is more stable than secondary, secondary is more stable than primary. So above product we can see, because it comes from the secondary carbonium ion, it is the most stable product, which is called isopropyl bromide. So in step 3, reacts with bromide ion to form isopropyl bromide as the major product. So in the same way, another example, the addition of hydrogen bromide to 2-methyl propylene. So here you can see tertiary and primary carbonium ions produced, in which tertiary carbonium ion is much more stable than primary carbonium ion. So the tertiary carbonium ion reacts with the bromide ion to give almost exclusively 2-bromo-2-methyl propane. Here you can see CH3C double bond CH2 plus HBr. So as it is forming this tertiary carbonium ion, where this bromine is added to the tertiary. So tertiary carbonium ion is more stable. So this forms the major product. Whereas you can see in the primary carbonium ion, the bromine added towards this carbonium ion is forming small amount 1-bromo-2-methyl propane. So when the 2 carbonium ions produced are about the same stability, almost equal amounts of the products are obtained. See, for example, you're taking CH3CH double bond CH2, CH3 plus HBr. It is forming secondary carbonium ion, and this is 2 also forming secondary carbonium ion. So you can see when it is attacked, it forms 2-bromopentane and 3-bromopentane. So that's all about this Markovnikov's addition of symmetrical alkenes. So next we are going to discuss about anti-Markovnikov's addition. See, this addition is also called as rash effect or peroxide effect. So you can see in the slide the scientist picture peroxide effect. So he only, and it is also known as anti-Markovnikov reaction. This is an organic reaction, and it was first discovered by Morris S. Rash in 1940. So it is an additional reaction, and the Rash effect is also called as peroxide effect. Rash discovered that the addition of hydrogen bromide to unsymmetrical alkene in the presence of organic peroxides, that is ROOR, takes a course opposite to that of the predicted by Markovnik's rule. So this is anti-Markovnik's addition, which is caused by the presence of the peroxide. So here we are using peroxide, which is called as Rash peroxide effect. So here we are going to take this propylene, which is an unsymmetrical alkene, which reacts with hydrogen bromide. So in presence of peroxide, mainly N-propyl bromide is the product, whereas in absence of peroxide, the main product will be isopropyl bromide. So here you can see the propylene, the unsymmetrical alkene CH3, CH double bond CH2 plus HBr. So in presence of peroxide, you can see it is forming anti-Markovnik's product. Whereas absence of peroxide, it is forming Markovnik's product, which is called isopropyl bromide. So the anti-Markovnik's addition of hydrogen bromide to alkenes also takes place when the reactants are exposed to UV light. And this mode of addition is not the reverse process of Markovnik's addition. And Markovnik addition in general, it follows ionic mechanism, whereas the anti-Markovnik's addition proceeds by free radical mechanism. See, in presence of peroxide, the anti-Markovnik's product is N-propyl, whereas in absence of peroxide, the product is Markovnik's product, which is isopropyl bromide, when it is taken as unsymmetrical alkene called propylene. So when you go in detail with the mechanism, so peroxides as well as UV light, which is able to initiate the chain reaction. See, since it follows free radical mechanism, we have initiation step, propagation step, and termination step. So the first step is chain initiating step. Here you can see the peroxide ROR, which can be dissociated to give two free alkoxy radicals, which attacks hydrogen bromide to form bromine free radical. See here RO dot, which is treated with HBr. So this pair of electrons, which is added to RO dot to form ROH plus Br dot. So this is forming a free radical Br dot. Then the hydrogen bromide on photochemical dissociation, that is when you pass UV light, it can give two free radicals. You can see the electron, which is carried over by hydrogen, and then another odd electron carried over by bromine to form free radicals H dot plus Br dot. So this is the initiation step. Next, the second step is the bromine free radical attacks the alkene, that is CH2 double bond CH3, which is called unsymmetrical alkene propylene, to form a secondary free radical. So the free radical of bromine carried over by carbon, and this bond, electron has been shifted over to this carbon, and this is shifted over. So you can see the secondary free radical, which is more stable. And the propylene CH2 double bond CH dot CH3 Br dot, it also can form free radical, the primary free radical, and which is less stable, whereas secondary free radical is more stable. So the more stable free radical formed from step 2 reacts with the hydrogen bromide. Here you can see the dot which is present in the secondary carbonium ion. You can see here it is attacked by this, and it is forming N-propyl bromide, which is called anti-Markovnik's product. So the N-propyl bromide Br CH2 CH2 CH3 plus Br dot, which is formed through anti-Markovnik's addition. So that's all about this Markovnik's and anti-Markovnik's addition. So we have seen with the hydrogen halide, especially hydrogen bromide. Whereas you can see you have hydrohalogens like HCl and HI. Whereas these two hydrogen halides do not give anti-Markovnik's products in presence of peroxide. Why? What is the reason? The HCl bond is stronger than HBr bond, and it is not broken by the alkoxy free radicals obtained from the peroxide. Whereas HI bond, see, it is weaker than HBr. So it is broken by the alkoxy free radicals obtained from the peroxide. but the iodine atoms so formed, it readily combines with each other to give the iodine molecules rather than attack the double bond alkanes. So this is the reason why HCl and HI do not give anti-Markovnikov product in presence of peroxides. So that's all about those Markovnikov addition and anti-Markovnikov addition. Thank you.